So on isometry of the Riemannian manifolds is a function where Mn or Riemannian manifold is a bijection that preserves the Riemannian matrix. So, if we think about, as I said, if we restrict two-dimensional manifolds, so think about M and N. Take a P, point P on a Riemannian manifold, and FP, that is, goes to F. And consider a surface tangent plane that map is defined by F star. As I said, in a Riemannian manifold, how we define a tangent plane with a k derivation, okay? And because if we consider that is two-dimensional, if we restrict two-dimensional, then that guy is that is correspond to plane. So we can think about two vector spaces, so-called, if we say that is V, and that is V prime, and the map in this case by F star, that is written as F star V, and that is F star V prime. So in that case, preserving Riemannian matrix means then when you compare to a definition of isometry, prime, or equivalently like this. In that case, that normed space is N, M, that is N, M, this key. Similarly, that means that isometry preserved the metric. Preserves the matrix. Important remark is that F in this definition, the map F is diffeomorphic, as a diffeomorphism. That means that F is 1, 2, and 1 on and on 2. Bijective. That is clear by definition, bijection, and its inverse is also differentiable. So the condition bijection is important to define an isometry. In the next definition, definition 5.6, I will explain the local isometry. Then compared to definition 5.6. In the later I will define a local isometry. Then here is the important part of in this lecture. As we see, isometry preserves the length, okay? But the important part is that isometric on a Riemannian manifold preserves geometry. Preserves the intrinsic distance. That is our main part of the lecture. That is not definition, that is theorism. Explicitly, for any Riemannian manifolds, take PQ in M, that is if you see in the image, if this is if P and Q is fixed, that if that is the shortest path length between P and Q, and by map F, that is goes to FP and FQ, and we can think about many arc lengths from FP to FQ. We can think about the shortest path, minimum path length between 2 points, is connected. Then intrinsic geometry is by the isometry. So how we prove this idea? Let alpha be a curve on M and alpha bar be a curve by F. So if you think about image, that is M, that is N, F, we can think about tangent plane mapping. Curve is given, that is alpha bar by constructing by map F. And we can think about a tangent vector that is alpha bar. And we can think about F alpha bar. In that case, that moves by, that is tangent plane. So alpha prime going to by map F star here, going to spew out. Okay. Can define F star alpha first, since F is isometry, the length is preserved. So okay, that is equivalent to alpha star, alpha bar, alpha prime bar. And that means that if we take point P and Q, when we consider any length going to from P to Q, whenever we choose a arc length, any arc length from P to Q, the length is same as any arc length between from FP to FQ. Which means that the arc length is same. But if when you consider our arc length runs from P to Q, and bar alpha runs from FP to FQ, F, as I said, is bijection. Since F is bijective, whenever we consider any path is given, when we collect the set, the collection of the L alpha is corresponded to arc length from L alpha bar. Okay? So, because this relation, when you take infimum L alpha is equal to infimum L alpha, because everything is corresponded to here. So when you take that is infimum one of the shortest path, that is we can correspond it to shortest path. And that is same. So we can desire result. What is desired result? Is that here. So intrinsic distance, not only a length from P to Q, the intrinsic distance, but also preserved by local local isometry, just isometry. Okay. Then what is a local isometry? Simply speaking, local isometry is isometry but bijective mapping. So that is mapping that preserves Riemannian matrix. As you see, that condition F needs not to be bijective. That fact that F needs not to be diffeomorphism. Because when we compare to the definition, because there is no need not to be bijective, okay, when you consider diffeomorphism, that condition is absent in a local isometry. F needs not to be diffeomorphism. But note that even though the map F is not bijective, by restricting the domain, we can make F restrict by domain U is a diffeomorphism. For example, in very, very easy example, when you consider cubic function in F R to R, that function is not diffeomorphism. Not diffeomorphism. Because the inverse function does not exist x equal to 0. When we compute this geometrically, if we consider inverse function at 0, as you see, where is it? Oh, f inverse function is defined by like this. So if we x equal to 0, that function diverges. So this is not diffeomorphism because the inverse function does not exist. But if you restrict the domain like this, that is diffeomorphism, because that area does not contain x equal to 0 point. So by restricting by the domain, f makes a diffeomorphism. That means that f becomes just isometry. That is, f is local isometry. Okay. Local isometry becomes isometry by restricting the domain. Proper domain. But proper. If we take this restriction, restrict this area, this contains 0. So this is not a nice proper domain. That is proper domain. Okay. That is the difference between the definition of isometry and local isometry. In fact, the definition of local isometry is more general definition than just isometry. Some important lemma is that local isometry preserves the first fundamental. That means that if a manifold M and N is given, if we think about E, F, G, and that exists also bar E and bar F and bar FG. That is because that is E is, for example, in case of two-dimensional XU dot product XU, like when you think about if F is a local isometry and F star is a tangent plane between TPM to TPN, that is described by okay, that is described by like this. Okay. In a similar fashion, we can describe F bar and G bar. Anyway, the local isometry preserves the first fundamental form. Case here, x in case of f, xu and xv is replaced to u f star v, like this. Okay, apart from a intrinsic geometry, there are many preserved by first fundamental form. Information of first fundamental form is preserved by local isometry. So definition, see the definition of geodesic. Geodesic is definition of geodesic is that if we consider curve alpha, and we can consider tangent vector, and if we derivative alpha prime tangent vector, we can consider 2 prime. And if in general, alpha 2 prime need not to be orthogonal, but if alpha 2 prime is always normal to surface manifold M, then we call M at the curve alpha is geodesic to M. For example, the geodesic is the easiest example is that the shortest path along the two curves is line. The shortest path on the sphere, two-dimensional sphere, is the great sphere. That is geodesic. That is similar to a intrinsic distance. So, like the intrinsic distance, geodesic is also isometric invariant. That means that geodesic is preserved by isometry in Riemannian manifold. Also, I explained in the previous lecture what is a Gaussian curvature. Okay, Gaussian curvature. Then so-called Theorema Regiorum, I don't know well pronounce, but that is very important theorism. What is this? Gaussian curvature is also preserved by isometry. So, apart from the intrinsic distance preserved by isometry, But Gaussian curvature and geodesic are also preserved by isometry.